Hi, welcome back to part 2 of our using graphs and charts for particle motion. So this question came from the 1998 AP exam. So we're going to take a look here. They're giving us the graph of the function of velocity. Remember, this is a velocity, which is a derivative graph. That's s prime of t. So the graph above, they tell us is velocity in feet per second of a car traveling in a straight road for the first 50 seconds. A table of values at 5-second intervals is given at a time. Chances are they're giving me, I think there might be some rate of changes here. We'll see. Is shown to the right of the graph. During what time is the acceleration of the car positive? Give a reason for your answer. Well, we know if we're talking about acceleration, we're really looking at the derivative of velocity. So what we're looking for is I'm looking for acceleration to be positive. I want my derivative of velocity to be positive. Remember, this is slopes. So I'm thinking first derivative test again. Oh my gosh. So the first thing we're going to need is the critical numbers. Where is acceleration or the derivative of our velocity equal to 0? So remember, we are going to look at the slopes of velocity. And it's easy to see. Be careful, it's not 0. Where is that slope 0? It looks to be up here, and that one time is going to, it looks like there's another one, almost missed one, where the slope is 0 here. So it looks to be at 35 and 45. So I'm going to write those down. T equals 35 and t equals 45 seconds. Do your sign chart. We're starting at 0, ending at 50, so we put our domain on there. We're looking at acceleration. So I just do my signs, 35 and 45. Now I could probably do this without a sign chart, but remember, we want to show our work. Looking at the slopes of the derivative, right? So between 0 and 35, the slope is positive. It's going up. Between 35 and 45, negative, and then positive. So accelerations increase positive, negative, positive. So if I want to find out where the acceleration is positive, I can now get it on the following domains. Get your answer from your sign chart. 0 to 35 or 45 to 50. And that is because v prime of t, which is acceleration, is greater than 0. Now, you don't have to put v prime t. You can just do a of t equals 0 or v prime of t equals 0. Sometimes we like to write it this way. We're crazy that way in mathematics. And that would be your answer. Piece of cake. Out there it is. What's the average acceleration of the car over the interval? Average acceleration, because they give me the graph here, well, to answer this question, well, how do we find acceleration? Well, you should remember this from your science courses. This is just change in velocity over your change in time. So let's see here. All right, change in acceleration over change in time. Well, what is change in velocity? Well, that's going to be the velocity at 50 minus the velocity at 0 over 50 minus 0. Now, hopefully you guys kind of reasoning that this looks to be like average rate of change. And it is our average rate of change. So let's go ahead and get this. V of 50, according to our chart, is 72 minus V of 0, which is 0. You're great if you don't turn your homework, over 50. And we get 72 over 50. We don't simplify. Don't worry about simplifying. Velocity is in feet per second. So this is feet per second over seconds time, which is going to be 72 over 50 feet per second squared. And there's your answer. Man, hard to believe these were on the AP. I mean, think about it. These were AP questions. Easy to do. The last one says, show that somewhere on the interval between 45 and 35, the acceleration is negative 3 feet per second squared. Well, now they're saying that it has to be exactly that, right? So, wow. So this is like my instantaneous rate of change. But this is giving me a range of values. So because they mentioned IROC, you know what I'm thinking? This is me, I'm thinking MVT. That's what I'm thinking here. So I'm going to find my average rate of change. Well, to get my average rate of change, acceleration, just like what we did up here, is the change in velocity. So it'll be my velocity at 45 minus my velocity at 40 over 45 minus 40. Well, what's my velocity at 45? Well, if I go up here, nope, there it is, it's 60, minus my velocity at 40, 75, and I'm going to divide that by 5. Oh, would you look at that? I get negative 15 over 5, which is negative 3 feet per second squared. Now, are they the same? Yes, but we're not done. You only get like a point for doing this. Now we got to answer it. Remember what I was thinking, MVT. So we would say, well, let's see here. Our velocity graph is continuous on that domain they gave us, 40 to 45, hard bracket, and differentiable on the open bracket, 40 to 45. Therefore, MVT applies, and because this is a little bit different, normally we would say, and therefore the slope would have to be negative 3. But we're going to write this one a little bit different. And because the average rate of change on that domain, 40 to 45, is negative 3 feet per second squared, at some point on that domain, 40 to 45, the instantaneous rate of change must equal negative 3 feet per second squared. Now, this is not the only way to write it, but let's take a look at what I'm mentioning, okay? 1, you have to mention the following: continuity on that domain, differentiability on that domain. You have to mention MVT. You have to mention that we got negative 3 at an average rate of change, and that's going to have to equal like for your instantaneous rate of change as well. Hope you guys enjoyed the video. I'll see you around for part 3 when we do calculators tomorrow. Bye-bye.